Hello, everybody. My name is Angela Pasquale. I'm professor at the University of Lorraine in France, and I'm honored to introduce the speakers of today's session on section 7, theory and generalization. And the next speaker is Professor Evgeny Feigin. He is a professor at the Department of Mathematics of the Higher School of Economics. And he received his PhD in mathematical logic, algebra and number theory from Lomonosov Moscow State University in 2005. And he received his Doctor of Science degree from the Institute of Information Transmission Problems of the Russian Academy of Science in 2013. He joined the Higher School of Economics in 2010, where he is currently the Deputy Dean for Research. His research interests are representation theory, mathematical physics, algebraic geometry, and combinatorics. And this is a live talk, and the title is PBW Degeneration, Quiver Grassmannians, and Toric Variety. Thank you.
So thank you very much for your introduction. It's an honor to speak at the ICM. And well, let me start. Let me give a brief plan of my talk. So first, I'll introduce the main player, the main object, the PBW filtration, the Poincaré Birkhoff Witt filtration. So this is a classical construction, and usually the filtration is applied to universal enveloping algebra of a Lie algebra. And the main idea is to somehow induce the filtration to a highest weight module. Well, I'll give the details below. So the construction is very natural and it has various aspects. So of course, representation theoretic aspect and combinatorial. And the important thing is that there is a rich geometry, namely the flag varieties. The classical flag varieties have their analogs in this graded or filtered theory, and we'll introduce the corresponding geometry in our talk. Well, these flag varieties, the degenerate flag varieties, are singular. Well, in general, and so they're related to several other objects like Quiver Grassmannians and toric varieties. So this Quiver Grassmannians description of the degenerate flag varieties in types A and C turned out to be very useful for both sides, for both directions. So this is a tool to discover and understand the structure of flag varieties, and also there are several results in the theory of Quiver Grassmannians obtained via this link. And so another direction is the link to toric varieties, to the theory of lattice polytopes. So of course the degenerations of varieties to toric varieties is a popular theme in the recent years. So it played a role in representation theory, algebraic geometry, in mirror symmetry, and many other mathematical theories, and also in mathematical physics. However, for us, it's going to be important the connection between combinatorics and the representation theory and toric varieties arising in this context. So before I start, let me first of all thank my co-authors. So Michael Finkelberg, Giovanni Cerulli-Irelli, Gislan Fourier, Peter Littleman, Marcus Reinecke for fruitful collaboration. So of course, this talk is based on joint works with them, and so it's an honor to thank them here. And also let me say that I would like to dedicate my talk to the memory of Ernest Borisovich Winberg, who passed away in 2020. And actually the discussions with him on monomial basis in irreducible representations of simple Lie algebras was very important for the start of the project. So let me introduce some notations. So I start with a simple Lie algebra, say SLN. This is type A case, but in principle, we can have here any simple Lie algebra, and even more generally, we can consider affine or other Lie algebras. So what's important is that this algebra is a class of highest weight representations. So namely, let us fix the decomposition G into the direct sum of H, N, and N minus. So say for SLN, these are diagonal, upper triangular, and lower triangular matrices. And we have irreducible highest weight modules, which are finite dimensional, V lambda. So here, lambda is a highest weight of our module. So it is dominant integral. So meaning that it's decomposed into the sum M1 omega 1 plus Mn minus 1 omega n minus 1, where n minus 1 is rank of G. So n minus 1 is the rank of G. And omegas are fundamental weights. MIs are non-negative integers. So any lambda can be decomposed in this way. And important feature is that V lambda is obtained from the highest weight vector by applying the universal enveloping algebra of n minus. So this is crucial for us. So this is the property of highest weight vectors, highest weight modules. And now by definition, we consider the induced PBW filtration on our V lambda. So the definition says that we take V lambda of S, this is a subspace in V lambda, which is the span of x1 up to xr applied to V lambda. So we apply no more than S elements from our n minus. So this n minus, well, in type A, is just lower triangular matrices. So we apply several operators. Well, the only condition is that we can't apply more than S operators. And then, of course, this is a filtration, the increasing filtration. And since the whole module is obtained by applying the universal enveloping algebra, the filtration exhausts the module. And we can consider the graded V lambda just by the standard construction. So please note that this is nothing but the induced PBW filtration, but the standard PBW filtration should be considered not on the whole G, but only on n minus. So if we consider the un minus of S, then the V lambda of S is the result of application of this un minus S to V lambda. So a remark, which is just a classical result, says that if you take the graded of this U of n minus, so this is the graded algebra, so this is nothing but just the symmetric algebra of n minus, and this is what is called the PBW filtration. PBW filtration. Or rather, PBW theorem. Okay, and so, well, we are now interested in the induced filtration. And so just a simple observation is that if you take the gradient of V lambda, then this is similar to the classical case, so this is the result of application of symmetric algebra of n minus to V lambda, and the symmetric algebra of n minus is nothing but a polynomial ring. So actually, after all, we are just interested in the quotient of the polynomial ring by some ideal E lambda. And well, what are the questions we would like to answer? Well, of course, what are the dimensions of the homogeneous components of our graded space? So this is the first point. And what is the I lambda? So, well, it's also interesting. And can we present a basis for V lambda? So what do I mean by a compatible basis is, so we take the positive roots F alpha of n minus. So alpha are all positive roots and F alpha are bases. They form basis of n minus. And then we consider monomials, monomial bases. We are just applying the product of F alpha S. So we're applying to V lambda. And so these S alpha are non-negative integers. And what we want to do, we want to specify what collections of non-negative integers we want to take in order to obtain a basis of our V lambda. And actually, well, we want the graded components to have bases composed by certain vectors from these bases. Okay. Now let me introduce the geometric counterpart of the story. So I take the group corresponding to the n minus. So this is the capital N minus, and the flag variety FL lambda is nothing but the result of the orbit of the line containing V lambda. So this is G applied to V lambda. So this bracketed V lambda is the line containing the high state vector. And what's important for us that the same object can be obtained as the closure of the n minus orbit. So of course the n minus orbit is smaller than the G orbit, but if you close, then you get the whole flag variety. And this is the projective variety inside P of V lambda. So now let's try to apply the same definition in our settings. So this is the degeneration procedure. So instead of considering n minus, we consider the Lie algebra n minus a. So as a vector space, this is the same as n minus. And we want to make it into a Lie algebra, just taking a zero bracket. So this abelian Lie algebra with the underlying vector space being n minus. And then, of course, it has a Lie group. So the corresponding Lie group is just the product of several copies of the additive group of the field. So this is denoted by GA. So this is GA to the dimension of n minus. Well, now the definition is very natural. So we just take this group, and this group is somehow an analog of n minus we had before. So we apply it to the high state vector, to the line containing the high state vector, and then we close. And this is a subvariety inside the projective space of V lambda A. So, this is a projective variety, and we want to study its properties more precisely. We want somehow to understand how does this variety look like. So more precisely, how to connect this FL lambda with FL lambda A. So this FL lambda is the classical flag variety, and this is its PBW degenerate version. So I want to describe the variety somehow. For example, in type A, So the varieties FL lambda have a very concrete linear algebra description. So I'd like to find similar one for the PBW degenerate version. So of course, we'd like to study geometry and topology of these varieties. So describe cellular decomposition, torus sections, and so on. And one more topic is, well, the description of toric degenerations, since, well, this is a tool for understanding the structure of the variety itself. So since toric geometry is rather well understood, so I'd like to use it for the description of the variety FL lambda A. So one important thing to note here is that it's known that the varieties FL lambda, the classical flag varieties, they depend only on the regularity class of lambda. So in particular, if lambda is regular, then this is the full flag variety. But well, it's absolutely unclear whether it still holds for FL lambda A, and in fact it does. So this is another evidence that the construction is natural and somehow interesting. So let us proceed. So now let me consider a special case. So this is the case, the type A case. So G is SLN and lambda is regular. So this means that lambda is the sum mi omega I, and all mi are strictly positive. So this is just to make the theorem, to make the claim more concrete. However, for G being SLN, we are able to describe the answer for all possible lambdas. So this restriction is not important, but we just want to make it more concrete here. So, for example, for regular lambda, the classical flag varieties are formed by collections of embedded subspaces. So V1 sitting in V2 up to Vn-1, and they are all subspaces of an n-dimensional vector space. And the dimension of Vi should be just I. So they just connect collections of embedded subspaces. So we want the theorem, which we are going to formulate in a minute, is an analog, so produces an analog of this description. So we take basis of an n-dimensional vector space, so E1 up to En, and then we introduce operators Pri of Ej. So these operators are projections with one-dimensional kernels, so they send Ej either to 0 if j is I, or to Ej itself is if j is non-I. So it has one-dimensional kernel, and so the kernels are linearly independent. So the theorem says that the FL lambda A consists of collections of V1 up to Vn-1. So the dimension of Vi is I. And so we are not insisting on the property that Vi sits in Vi plus 1. So we are not saying that should hold, but instead we are saying that if you apply the operator Pri plus 1 to Vi, then the result should sit in Vi plus 1. So this is some algebraic condition, and so the varieties defined in this way are singular in general, but it turned out that they're normal and irreducible. So this is absolutely unclear from the definition. And what is clear is that they are so-called GA varieties. So these are kind of additive analogs of toric varieties. So that means that there is a group GA to n minus 1 over 2. So this n minus 1 over 2 is the dimension of the subalgebra of low triangular matrices. And this group acts on our FL lambda A with a known open orbit. So just by definition, the variety itself is a closure of the orbit of this group passing through the highest weight line. So let us proceed. So with an example. So this example is the first non-trivial example. So we consider n equals 3, so SL3, and then we have pair of subspaces V1, V2. So V1 is one-dimensional, V2 is two-dimensional, and we have the only condition for these two subspaces in a three-dimensional vector space, saying that there is an operator PR2. So actually here, this PR2 is any operator with one-dimensional kernel. If you apply it to a one-dimensional vector, the one-dimensional vector space, you have to land in the two-dimensional vector space. And so how to describe this variety in a more concrete way? Since V1 and V2 are subspaces in a three-dimensional space, one of them is one-dimensional, another is two-dimensional, then both are elements of P2, projective plane. And let us denote by x0, x1, x2 the coordinates in the first P2, and y0, y1, y2 the coordinates in the second P2. Then this FL lambda A is cut out by a single relation, x0, y2 plus x2, y0 equals 0. So this is the relation. And the difference with the classical case is that we don't have the middle term x1, y1, which is present in the classical situation. So you can see that this is indeed a degeneration where you just somehow kill the central term x1, y1. So, well, these varieties, they are singular, but still nice. So, it has a nice topology, and in particular, one can describe the cells in terms of combinatorics of Genocky numbers, of the median Genocky numbers. So this is a replacement of the n factorial, which is the cardinality of the Weil group of type A. Well, the varieties have various interesting properties, and one way to study them is to interpret the linear algebra description as a description of a Quiver Grassmannians. So one can recognize that this description as a sequence of vector spaces subject to certain conditions is somehow in the spirit of the definition of Quiver Grassmannians. So namely, let us take Q to be the equi-oriented type A n-1 quiver. So we have n-1 vertices and arrows between them, all pointing out from, say, left to right. And a representation of this quiver is a collection of vector spaces. Let us take a very, very special case. So where all vector spaces are of dimension n. There are also maps between these vector spaces, f1, f2, up to fn-2. So linear maps between n-dimensional vector spaces. And in order to define the corresponding Quiver Grassmannian, one also has to specify what is the dimension vector. So D, let us fix D to be 1, 2, up to n-1. So this is the dimension vector. And to this data, we attach a Quiver Grassmannian. So this is denoted by gr underline d of m. So these are subspaces, collection of subspaces Vi in our n-dimensional vector spaces. So remember that to each vertex we associate an n-dimensional vector space, and inside these vector spaces we take our Vi's, and the dimension of Vi should be I. So because the components of our D are exactly I, well, the Di is I, and the condition is that Fi of Vi sit in Vi plus 1. So actually the examples we had before, they are of this form. So for example, if AI is just the identity operator for each I, then the corresponding Quiver Grassmannian is nothing but the full flag variety SLN mod B. So this is just by definition. And if we take Fi to be projection I, then what we get is the degenerate flag variety. So you can see that it's reasonable to consider all possible maps, all possible Fi's, and to consider the Quiver Grassmannians of this form. So, this means that we are getting a connection between the classical flag variety and the PBW degenerate flag variety. And actually one can construct in this way a flat family over A1. So a flat family of varieties. So each member of the family is going to be a Quiver Grassmannian. And so in our situation, this general fiber of the family is going to be a classical flag variety, and the special fiber is going to be a degenerate flag variety. So of course, we can consider a family not over A1, but over all possible maps between the n-dimensional vector spaces. And this is going to be a very interesting family, and we were able to derive certain results of this. Let's move on to the toric varieties part. So actually, there are two different objects we are going to study here. First of all, this is the combinatorics of the basis of representations V lambda A. So remember, these are PBW degenerate representations. So being the direct sum of the components, the graded components labeled by the number S. And so we want to, as I mentioned at the very beginning, so let me get back to that slide. So this is the questions we formulated. So we were wondering whether there is possible construction of monomial basis for our representations, and the monomial bases are going to be labeled by the numbers S, by the collections as alpha. Yes, so we are given a lambda, which is the dominant integral weight, and given such a lambda, we want to say what collections of non-negative integers as alpha, so alpha being positive roots, we have to take to obtain a monomial basis. So, this is the natural and expected construction that there might be some nice polytopes describing this basis. So namely, the S alphas we are going to take are integer points in some polytopes. However, what's important here that these products of F alphas are considered as elements in the symmetric algebra. So therefore, well, we don't care about the order, and in fact, we only care about the numbers S alpha themselves. So the one more important thing is that we want this basis to be compatible with our filtration, meaning that if we take the sum of S alpha to be equal to some constant, say S. So so if the sum of S alpha equals S overall alpha, then the corresponding vector should produce the basis of the homogeneous graded component. So let me describe the answer. So, and let me introduce, first of all, a piece of notation. So I denote by Fij, where I and j are between 1 and n minus 1, basis for n minus for the low tangle matrices for SLN. So these Fij, they are attached to positive roots. The positive roots are alpha ij. So they're given explicitly by alpha I plus 1 up to alpha j. And then we have the corresponding root vector, Fij. For example, if I equals j, so this is just one, we have one summand, alpha I, and this is a simple root. And the corresponding Fii is the simple, is the root vector corresponding to the simple root. So you can see in the example, the case of SL5. So if we ignore the green part of the picture, then this is just the picture, well, for the 10 roots of 10 positive roots of SL5, starting from alpha 1, 1 to alpha 4, 4. These are simple roots, and then alpha 1, 4 is the highest root. And then we need the notion of a dig path. So what are we doing? So here you can see an example of a dig path. This is a collection of several positive roots. So we start with the simple root, alpha 1, 1, for example. So it doesn't have to be alpha 1, 1. We can start with alpha 2, 2 or whatever. And then we move either down right, or we move up right, and moving this way. So we are getting a collection of roots. So here we have 7 roots, and this is a dig path. So we denote by S of P the starting point of our path. So here it's alpha 1, 1, and by T of P we denote the terminal point of our P. This is alpha 4, 4. So, well, why do we care about the dig path? So this is the combinatorial object which is going to somehow specify the polytope, or as I said, going to specify the basis we are going to construct. So let me state the theorem. So let me take lambda to be the sum of omega i's, the sum of fundamental weights. So the coefficients mi are going to be non-negative integers. So we don't impose here the condition of lambda being regular. So this any lambda, so mi are non-negative. So then we want to say what are the monomials Fij raised to the power Sij, such that if we apply such a product to V lambda, then we get basis of our module. So once again, let me stress that the order of factors in this product is not important at all. So we only care about the number of Fij's involved in this product. And so, well, what are the conditions? So the conditions are written in terms of dig path. So we take a dig path P, and we associate to any such a path a condition saying that if we take all ij's such that alpha ij belong to P, then the result, and we sum up all sij's with this condition, then the result should not be larger than the sum of the coefficients of lambda, and then this is m s of P plus m s of P plus 1, and then up to m t t of P. So once again, let me say that, let me repeat that the number of conditions is equal to the number of dig paths. So we have lots of conditions. So let me give an example. So let's take G being SL3, and then we have three positive roots, alpha 1, 1, alpha 2, 2, and alpha 1, 2. And we take F11 raised to the power S11, we take F12 s to the power S12, and F22 to the power S22, and we apply it to V lambda. And so we want to know when this is a basis. And the conditions say that we want S11 to be less than or equal to M11. So this corresponds to the dig path of length 1, and then similar to for the second simple root. So S22 is no larger than M2, and then the sum of three, S11 plus S12 plus S22, should not exceed M1 plus M2. So this is the only length 3 dig path here. So, well, the theorem gives us a basis for the graded space, for the degenerate space V lambda A. However, well, since this is a basis for the graded space, is also a basis for the classical space. And well, of course, in the classical situation, Fij do not commute. However, you take a monomial from our basis, and then you order the Fij's in any way you want. So just absolutely arbitrarily. And then this produces a basis for your model. So actually this is a family, a huge family of bases for the classical models. So let me introduce a notation. So I want P lambda to be a polytope defined by the dig path conditions. So P lambda is a subset in R to the power n times n minus 1 over 2. So let me show you once again. Here the conditions. So you can see that our polytope P is formed by collections of numbers Sij. So if we want to consider the polytope in the real vector space, so we don't have to insist that Sij are integers, but these are arbitrary real numbers. So and we take the conditions, the same conditions. Well, the conditions are labeled by dig path, and so our polytope is defined as a subset inside R n minus 1 over 2. Actually, we can even say that since all the coordinates are non-negative, so this sits in R greater or equal to 0 to this n minus 1 over 2. So note that the Sij's, as I said, they are integers. So we can say that the bases we've considered in the previous slide are labeled by integer points inside the polytopes P of lambda. And so, well, of course, given a polytope, a convex polytope, one can associate to this polytope the toric variety. So the toric variety inside projective space, so projective toric variety. And so let me write it here. So projective toric variety. So far we have no connection between the flag variety and this toric variety, but it turned out that actually there is a flat family, flat degeneration from this FL lambda A to X P of lambda. And this toric variety actually is rather nice. So we can describe it since we have an explicit form for this polytope. You see that we derived the corollary that the classical flag variety can be actually degenerated to this toric variety corresponding to P of lambda, and the degeneration somehow factors through the degenerate PBW degenerate flag variety F lambda A. So the most kind of most well-known degeneration is a degeneration to the Gelfand-Zetlin polytope, and this degeneration is also very explicit and nice and can be used in many applications. So let me mention several open questions, open directions in this theory. So first of all, I mentioned that the concrete results stated above are mostly about type A case, so G being SLN. So also there are certain results available in type C. So there's an explicit description and there are polytopes, and so this can be studied and described. But for orthogonal Lie algebras, the information is not actually, so such a description, such a concrete description is not really available. So let me mention that it would be interesting to somehow consider the orthogonal Lie algebras as well as the Lie algebras for other simple types. So also there are some infinite dimensional analogs which are kind of very interesting, and so they deserve to be studied. So these are semi-infinite flag varieties, so obtained by replacing the base field with the ring of Taylor series in one variable, for example. And some results in this direction are also available. However, this is not too much is known, and many questions to be studied here. And of course, there is a representation theoretic counterpart for this semi-infinite world. So these are current Lie algebras. So these are tensor products of simple Lie algebras with polynomials in one variable. These algebras have nice highest weight modules. So the analogs, highest weight modules, the analogs of them. And of course, there is the case of affine Kac-Moody Lie algebras and affine flag varieties. So these are int varieties, and the corresponding representations are infinite dimensional. However, integrable representations of Kac-Moody Lie algebras are also well studied and are also very interesting, and it would be nice to obtain results in this direction as well. So that's all I wanted to say. Thank you very much for your attention.
Thank you very much, Professor Feigin, for your interesting talk, and thank all the participants for their attention. Goodbye.
Thanks.